Professor Will Oliver, who is the Harry Willis Heron Professor of Electrical Engineering and Computer Science at Lincoln Labs as part of MIT. And he will tell us about giant artificial atoms and molecules, chiral photon emissions via quantum electrodynamics.
Yeah, thanks, James. Really appreciate the introduction, and thanks, Bill, for the invitation. Really glad to be here and talk about some of our research that we're doing in the Engineering Quantum Systems group. Before I get started, let me recognize some collaborators in Nakamura's group in Japan, also Franco Nori, Anton Kokum. They're also in Japan and Sweden now, and Yuri Vinet and Charlie Tahan. And I'd like to talk about some experiments with superconducting qubits, but we're going to call them artificial atoms. And in fact, we'll call them giant artificial atoms. So to define that terminology, let's think about what a small atom is. That's the usual atoms that we think about. They're small in the sense that if we wanted to drive a transition in the atom itself and its spatial extent is small compared to the wavelength of the light that we're using to drive it. So this allows us to make with the dipole approximation. And you can think of it as an atom or a qubit connected to a control line in one place only. And most of the atoms that we think about in life are this way. So if you have a natural atom from the periodic table, it's about an angstrom. We drive it with optical light, maybe 100 to 1,000 nanometers. And so the ratio of those two is 1 in 1,000, 1 in 10,000. Now, there are these things called Rydberg atoms where you excite the atom to a highly excited state, makes it much, much larger, and you might think, okay, that's a giant atom. But in fact, it's even deeper in the small atom regime because when we have that large atom, now 10 to 100 nanometers, we're now driving it in the microwaves. And if you look at that ratio, it's now 1 in 10,000 to 1 in a million, so even smaller. Superconducting qubits, though, you can see them with your eye. So they're quite large, 100 microns. And we also drive them in the microwave. And nonetheless, you take this ratio, it's 1 in 100, 1 in 1,000. So a superconducting qubit is also a small atom. But we have some flexibility with superconducting qubits in that we can make them look like giant atoms. So giant atom meaning its spatial extent couples to the wave that's driving it in more than one place, or in multiple places. And we can do that because we basically make electrical circuits. So we can draw wires from our qubit to the control line and connect it in different places. And now you think about trying to drive this atom, the dipole approximation doesn't work. Classically, the atom is not following the electric field anymore. How does it follow it? Because it's coupled to it in multiple places. Which one do I follow? So this, of course, leads to quantum interference, self-interference, and it means dipole approximation is no longer valid. So what we're going to do is we're going to leverage the large size of superconducting qubits, our ability to connect it in multiple places, and quantum interference to realize high-fidelity operations in waveguide QED. That's what we want to do. So the first topic will be waveguide QED and giant artificial atoms, just the initial demonstration. And this is work done by Bharath Kannan, who's now CEO of Atlantic Quantum, a startup, and Dan Campbell, who was a postdoc and is now at AFRL in Rome. So superconducting artificial atoms are basically qubits, but they start off life as a LC circuit. And this is a harmonic oscillator. You might recognize this as parallel LC circuit with a resonance frequency 1 over the square root of LC. And if you cool this down to low temperatures, in fact, it is a harmonic oscillator, and so it will have discrete energy levels, and those levels correspond to counting the number of excitations of this circuit. So this doesn't happen at room temperature, but if you cool it down enough, this is a quantum circuit, but it's not a qubit. And the reason it's not a qubit is because the transitions between 0, 1, 1, 2, 2, 3, they're all degenerate, right? And so I can't live only in the 0, 1 subspace without exciting all the levels. So what we need to do is something else, and that something else is to introduce a nonlinear element. Here it's called a Josephson junction, and for the purposes of this talk, it's just a nonlinear inductor. It's two superconducting leads separated by a thin insulating barrier, and Brian Josephson basically gave us these two constituent relationships for the current and the voltage of this device. And when we combine them in the usual way to to define the inductance, we find the inductance is nonlinear in the current that flows through that device. So it is a nonlinear inductor. You could even calculate the energy and find out that it depends on the phase as a cosine. And so if we make that same LC circuit using the nonlinear inductor, we find now that the potential profile, rather than being quadratic or harmonic, is in fact a cosine. And what that means is that the 0-1 transition frequency now differs from the 1-2 and the 2-3. Okay, so now we can live in just the 0-1 subspace, drive that transition without exciting higher levels if we're careful. Okay. So many artificial atoms are built from this concept. This one is called the fixed frequency transmon. And we're going to use a variant of that in these experiments. Now, the second term to introduce is waveguide QED, and that is a variant in some sense of cavity QED. So cavity QED has been used in quantum information for a long time, and it's basically a way to protect atoms from this environment. And the way that we protect it is by putting it inside a cavity. Now, in the environment, there's a quasi-continuum of modes that would love to take the energy from my atom. And one way to protect it is by putting it in a cavity, I now have a discrete set of energy levels. Now, if my atom is on resonance with one of those energy levels, I actually enhance the spontaneous emission. It happens faster. That's called Purcell effect. But if I detune my atom from those cavity modes, I'm actually protected. And we take advantage of that in superconducting quantum computing in particular. It is the dominant architecture today to protect qubits from their environment so that they're long-lived. Okay, so then you might say, well, that sounds great. Why are we going to go back to waveguides? Waveguides seem like a really bad idea because I'm coupling qubits directly to a waveguide which has a quasi-continuum of modes, which it wants to take the energy away. And the reason is that our application that we're interested in is to make a quantum interconnect. We want the qubit to emit a photon. We want it to emit it quickly, go down a waveguide to another place, and get absorbed again. We're making an interconnect for qubits or for qubit processors. And in that case, we don't want the cavity mirrors there because that's going to just interrupt. Photon will bounce around many times before it actually leaves. Okay. But there's no free lunch. In waveguide QED, we have some challenges. So one is that there's an always-on dissipation. It's always trying to take energy away. How do we control our qubits in the presence of that dissipation, but still do something useful? So, and then the second question is, can we engineer interactions that are mediated by this waveguide also while avoiding the dissipations? And we will answer these two questions. Okay, so maybe one more thing about coupling atoms to propagating photons. If you are in free space and you have an atom and you want to drive it, you could think of driving it with a plane wave. And the plane wave would excite the atom or the qubit from the ground to the first excited state. And then when it emits spherically. It emits in all directions. And what we find is that, well, okay, this looks very pretty. It's an interference pattern between the incoming and the outgoing waves. But it's not so practical. And what we would say is that this is a poor spatial mode matching. What's coming in doesn't look anything like what's going out. And if I wanted to capture all those photons, I need to position detectors everywhere in there. Okay. Now, with superconducting qubits, we have an advantage in that we're coupling it to a one-dimensional waveguide. And that means there's really only two directions to go, forwards and backwards. And so if we drive this qubit coupled to this waveguide, we send in a wave this way. It excites the qubit. The qubit will emit a photon, which goes backwards and forwards. That's every direction from a one-dimensional perspective. And what we find is that if we're in the one photon or less than one photon limit at a time arriving at this atom, the forward scattering is completely suppressed by quantum interference, and the reverse scattering is enhanced. Okay. And this is just to say that there is a big advantage to working in one dimension. Okay. Now you might wonder, what about cooperativity? Can we get into the strong coupling limit? Well, in the case of cavity QED, of course, you have the Q enhancement of the cavity, and you also have the matrix element, but we don't have a cavity, right? So you could just think of that as one, order one. But with superconducting qubits, we can basically couple it as strongly as we want to this waveguide. And so we can still enter the strong coupling limit, where exchange of energy between the qubit and the waveguide, that rate is much larger than, say, any other non-radiative relaxation time. So we are in the strong coupling limit. Okay, so with that, the experiment we do looks something like this. We've got qubits, and we'll couple them to our waveguide. They exchange energy at a rate gamma. The qubit frequency is omega. And then it, of course, loses energy to other degrees of freedom, not just the waveguide. Getting one step closer, you could schematic this as a qubit. Now, you see here there's two Josephson junctions forming a squid. And we do that because by putting a magnetic field through that loop, we can tune the qubit's frequency. That's useful. When it's at 20 millikelvin in a fridge, we would like to be able to have a knob at room temperature to change its frequency. Okay, but otherwise, you can see that this is an inductor in parallel with a capacitor. And it's coupled to a 50 ohm transmission line. Illustrated here is a coax cable, but that's not what we're going to use. What we actually use is a coplanar waveguide. It's a center strip. Here's ground. So the center signal line is in black. There's a silicon field in white, and then the ground plane is also in black. So that's the coplanar waveguide. We capacitively couple to it from our qubit. This is the capacitor of our qubit. It's a lateral capacitor. It's side by side, not parallel plate. And then zooming in here, you can see this is our inductor, which is in the squid format. And we put a magnetic field through it to tune the qubit frequency. So that is our device. Okay, so just to show that this all works, what we can do is at 20 millikelvin, we have our qubit chip. Here's the waveguide, couples to a qubit. And at room temperature, we have a network analyzer. And that will send a signal out port 1, comes in here, interacts with the qubit, and then the signal continues, gets amplified, and goes to port 2. But remember, what I said is that if we're not too strong of a field, the average photon is less than 1, then all of the energy should be reflected, which means none of it should pass through and arrive at port 2 when we're on resonance. And that's exactly what we see. So what we're doing is that 0 here is the detuning, so that's on resonance. And when we're on resonance and we look at what arrives at port 2, it's less than 1 part in 10,000. Almost nothing arrives there. Detune it just a little bit, and now a lot of photons are going through because they're not absorbed by the atom. And you can look at this in a 2D plot where we're plotting the detuning as well as the probe power, and this dashed line here is what we're taking. I won't explain too much about that, but just to say that, yeah, okay, if we're on resonance and we increase the power that we're applying, eventually we start to see energy appearing at the second port because basically more than 1 photon is arriving. While the atom is interacting with the first photon, a bunch of other ones just run right by and end up at port 2 of my network analyzer. Okay, so this is all working the way we expect. Okay, so let's make it one level more complicated. We're going to braid 2 of these giant atoms. We have 2 qubits, A and B, and we attach them or couple them to the waveguide at specific points. And we can define the distance between these points in terms of phase. So what is that phase? Well, it's the physical distance between the qubits, that's delta x, divided by the velocity of a photon at that frequency here. It's about 1/3 the speed of light, times the frequency of that photon, which is same as the frequency of the qubit that emits it. Okay. This is what the circuit looks like on a chip. The 2 qubits are in yellow, shown here. And then the blue is the waveguide, and it meanders back and forth, but you can see that it hits each qubit twice before it leaves, right? So each qubit is coupled twice to that waveguide, and they're interleaved. Okay. And if we zoom in, this is the capacitor. It's a different shape than the square I showed before, but it's still the capacitor coupled to the waveguide in 2 places. We can control the frequency. We had a feature here where, just for experimental control, we used a conventional way to read it out as well, just to double check, but that's not part of the experiment. Okay, so the first thing we can demonstrate is that we can basically turn off dissipation to the 50 ohm environment. So we terminate these in 50 ohms. This is a 50 ohm waveguide. We're going to forget about qubit B for a moment. We'll just detune him in frequency. And we're just looking at what happens with qubit A. And we'll put qubit A in its excited state. And when we do that, it can emit a photon, and that can happen in a few different ways. One way is that it could just emit from this point to the 50 ohm environment, okay? Or it could emit on this side instead, and the photon has to travel all the way around to get to the 50 ohm environment. And it picks up a phase of 2 phi in doing that. So this basically starts to look like an interferometer. And if I pick the correct phase, I could have this process destructively interfere quantum mechanically so that it doesn't happen. Okay, and remember that phase is determined by the frequency of my qubit. Now, you might say, oh, there's another 50 ohms over here. That's true, but the process works in either direction. And so by picking the right phase, you basically can turn down the dissipation, this is the decay rate, gamma 1, to the 50 ohm environment. And what we see is that it's minimum at this one point. And if we detune the frequency, then of course it's going to increase because this destructive interference is no longer perfect. Okay, and if you prefer to look at things in the time domain, here's the decay traces. This T1, the longest was about 30 microseconds in this case, which is consistent with a qubit that wasn't coupled to any waveguide at all. Okay, and then as we detune the frequency, it gets larger and larger, or the T1 goes down, the decay rate. Okay, so we answered the first question. We can in fact turn off the dissipation to the environment. Now, the second question is, can we couple these qubits together while also being decoupled from the environment? And so I won't go into the physics behind this today, but just to say that these qubits do couple to each other, and they couple in this way. It's of course related to the rate at which they're coupled to the waveguide. Turns out it's gamma over 2 times sine of this phase. And pairs of points will couple, right? So here are 2 points between A and B, another 2 points between A and B, and another 2 points between A and B. And then, of course, there's one more pair, the outermost, and they're separated by 3 phi rather than 1 phi. But they all have the same gamma over 2 in front. Now, this is a coherent quantum mechanical process. So each of these paths will add together. And so the net coupling strength is actually all 4 of these paths. Okay. Now, if we take one of the qubits, hold it at a fixed frequency, take the other qubit and sweep its frequency, when they're on resonance with each other, they interact. And an avoided crossing opens up of a strength. Here it's 2g over 2 pi. Okay, so they do in fact interact with one another via the waveguide. But what's quite interesting is that that coupling can occur over quite a range of frequencies, including the one where they don't see the 50 ohm environment. So we're interacting 2 qubits with one another via the waveguide, but they don't see the 50 ohm termination. So this is quite useful. Okay. So we can engineer this coupling spectra in a few other ways. First is the number of coupling points. We just looked at a qubit coupled at 2 points, and it had 1 minimum in the decay rate. But I could couple it at 3 points, and it turns out that it'll give me 2 minima. 4 points will give me 3 minima, etc. Okay, so that's one thing I can do. Another thing I could do is these coupling strengths need not all be the same. I could tune them relative to one another. And the impact that that has, the ratio of gamma 2 to 1, where this is gamma 2, you can see that by increasing that ratio, if you think of that as a double well, it's suppressing the barrier. Okay. And of course, the third one is that I can move my qubits around. I don't have to have them equidistant. So in the experiment that we used to demonstrate the giant atom, we used a coupling of 3. So each qubit is coupled at 3 points. The size of the circle here indicates the strength of the coupling. And you can see that the distances are not all equal. Now, this is what the circuit looks like. We again have 2 qubits, and the waveguide meanders back and forth, but now it'll hit each qubit 3 times, okay, coupled at 3 points. Okay, these are the numbers, in case you're interested, in terms of the phases or distance between the qubit, as well as the relative strengths. And so now, when we look at this, we can map out that, in fact, the decay rate now does have 2 minima, as we wanted, because we've coupled at 3 points. And if we look at the coupling between qubits when they're resonant, it can be designed to be the same at these 2 decoherence-free frequencies. Okay, so the experiment then was, let's see if we can create an entangled state. All right, so we have 2 qubits, qubit A and qubit B, and we park each one at their own frequency. When they're not at the same frequency, they don't talk to each other. But each one is isolated from the environment. We'll then, okay, we start them both in the ground state. We then put a pi pulse on qubit B, so it's in the excited state now. We'll then shift the frequency of qubit A up to the frequency of qubit B. They're now on resonance, and they're going to exchange energy with one another for some period of time until we shift qubit A back down and park it at its own decoherence-free spot. And then we'll do readout and ask, what state are you in? And what we find is that we get, in fact, this exchange interaction or swap type interaction between the two qubits. And you can see that by the bright spot here corresponds to a dark spot, and then it toggles back and forth. So if we take a slice when they're both truly on resonance, then you can really see these oscillations. And they are, juxtaposed with one another. And to make an entangled state, the idea is to do half a swap, or square root of swap as we call it. And when we do that, we create this entangled state 0, 1 minus I 1, 0. We can then do state tomography. And what we find is that we were able to do this with about 94% fidelity. Now, that's not a world record. Some of the best 2-qubit gates are now more than 3 nines with superconducting qubits. But we have to remember that these 2 qubits are both strongly coupled to a waveguide. If we didn't do all these tricks, it would have decayed within about 10 or 20 nanoseconds. We wouldn't even have been able to prepare this first pi pulse with any reasonable fidelity. But we can do it because these are giant atoms and we play these tricks. Okay. So we can entangle qubits despite the strong coupling to the open environment. Okay. And that becomes a tool that we'll now use. So the tool, the use is to show directional photon emission so that we can send a photon deterministically to one place or another and then catch it. This is work by Bharath and also by Dan. So towards these quantum interconnects. So we would like networks of quantum modules. We like modularity. Systems are built upon modules. And we need to distribute the entanglement between different modules. So there are a couple examples of interconnects today with superconducting qubits. One is based on a cavity. You make a cavity, you couple qubits to that cavity, and the pros here are that these have given the highest fidelity so far. They are bidirectional. I can send a photon right or left. But it's limited in terms of how long this cavity can be. If I make it too long, the free spectral range goes down. The separation between cavity levels goes down and becomes a problem. The other way you could do it is you can couple via a single-ended waveguide. So this is like waveguide QED. But to get rid of the unwanted dissipation, and they end up putting in one of these isolators or directional circulators, and they tend to be pretty lossy and they're quite big, and this just isn't really extensible. So we were wondering, is there something else that we could do based on quantum interference? So the idea now is rather than just making a giant atom, let's make a giant molecule. Okay. So the molecule comprises 2 artificial atoms, qubit 1 and qubit 2, and we're going to put them in an entangled state. Now I'm going to use E and G for excited and ground state. And importantly, we're going to change this phase, but let's just look at this particular example, pi/2 phase shift. Okay. So if we couple these two, or single molecule now because it's entangled, to the waveguide, but we do it at different points, then we're also going to get emission and quantum interference. And so the idea is, how does that happen? Well, there are a couple different pathways by which it can happen. So one of them is that qubit 1 was actually excited and emitted its photon, and it emitted it to the right. And if we're bookkeeping how that happens, there are 2 phases. One is the qubit state phase. Well, this is e to the I0, so we'll just call it that. And the other is the position phase. Well, I'll just call that x equals 0, and so now that's e to the I0 as well. And the 0, 1 means 0 photons went left, 1 photon went right. Of course, in an entangled state, it could have been qubit 2 that was excited, and it emits its photon, and it could have gone to the right. And in that case, the phase is now e to the I pi/2, so that appears here. And given the convention of how we do things in physics as opposed to engineering, we're going to say that this is pi/2 away, and it comes in with a minus sign. Okay. Now, I won't talk through the leftward one, but it's the same story. Qubit 1 could have emitted that photon to the left with these phases, or qubit 2 could have emitted it to the left with these phases. But what you find is that, interestingly, these two perfectly and destructively interfere. So I'm only left with a photon that goes to the right. So by choosing this phase of this entangled state of my giant molecule, I can say, photon, I want you to go to the right. Now, there's one thing that you might be wondering, which is we just talked about how these two qubits couple to each other via the waveguide. Absolutely true. And that would ruin this picture that I just described. And so what we need to do is we need to couple qubits 1 and 2 in a controlled way that's exactly equal but opposite sign of the coupling through the waveguide. And we do that, and when we do, this simple quantum optics picture of photon emission holds. It's the same story on the other side, but what I do is I change this phase from plus pi over 2 to minus pi over 2. And when I do that, it's now the leftward photon that survives and the rightward photon that destructively interferes. So I have a way to deterministically send a photon either to the right or to the left. Okay. So we end up doing this in what we call an emitter module. The two qubits that I just talked about are what we'll call emitter qubits, and they emit to this waveguide. But I want to prepare the entangled state and couple it to a processor node. That's my future application. So I'm going to add 2 more qubits here, 3 and 4. I'll create the entangled state that I then shuttle down to the waveguide, right? And then when I absorb, I'm going to bring it back in and store it here, and eventually couple it to some other processor that's local to it. So I need to couple these 2 qubits together so that I can create an entangled state. And the idea is once I have that and I'm ready to send it to the waveguide, I'll couple 3 and 4 simultaneously down to 1 and 2. I shift the photon down and then it goes. And it'll go left or right depending on the phase that I chose. So this is what the device looks like. You can see these 2 qubits up top in pink. That's qubits 3 and 4. Their coupler is shown here. Qubits 1 and 2 are at the bottom. They're coupled to the waveguide. Here's the coupler that nulls out any coupling via the waveguide. And then here are the 2 shuttle couplers. Looks a little complicated, but it actually works. It's 8 qubits total. And if we want to generate a photon, this is basically what we do. We start with all of our qubits in the ground state. We will put qubit 3 in the excited state, for example. We then drive an interaction between 3 and 4. We'll do the square root of swap gate again and create the entangled state here. And when we want to shift it down, we drive these couplers and we shift that entanglement from the top qubits to the bottom qubits. And when they reach the bottom qubits, they then emit their photon. In this case, let's say we chose it to go to the right. Okay. So here's an example of a photon that is only going to the right, but not to the left. And here's one where it's going to the left, but not to the right. So just to show that this works, and these measurements are made at room temperature, of course. And just to mention that we're actually measuring the voltage because we want to measure these field amplitude operators so that we can then build up any order of correlation function that we want so we can do tomography. Okay, so we're not measuring the power, we're measuring directly the amplitude. So we can do that tomography. You can see those correlation functions here at the bottom. And what we find is that when we send the photon to the right, by and large, that's exactly what we see, is that there's a photon on the right. And when we send it to the left, there's a photon on the left. We do that with almost 95 or 96% fidelity. So of course, we'd like that to be 99. We're working on that. But this is already pretty good. So the next step then is to show that this modular network works. And this is work that's done by Aziza and Beatrice. So the idea here is I don't need to have just one of these modules. I could have many of them, and they're all coupled to some local quantum processing unit. And I'd like to entangle or have these processing units talk to one another. And I can do that by connecting them in an all-to-all manner along a single waveguide. And that here I'm showing it linearly, but it could wind back and forth. This could be 2-dimensional, could even be 3-dimensional. Okay. And the idea is that I'll send a photon from the emitter and I'll send it to this module, which is the absorber. And one nice feature of this, which is from the Nakamura group, is that all I need to do is run this one backwards from the procedure I use to emit it, and I can absorb it. So it's the same module. I could then do a different one here. And so any combination or pair of these can send photons to one another. Okay. So in the experiment, we have 2 interconnected modules. This is done in kind of a first try kludgy way, but it actually worked pretty well. We've got two modules connected by a coaxial cable. And we're going to send the photon from the left to the right, and then we'll send it from the right back to the left. So this first module is in package 1, which is on this side of a thermal finger at the mixing chamber of a dilution refrigerator. Package 2 is on the other side. And then you can see the coax. It's a niobium titanium coax, which basically just looped around and connected them together. Lots of loss in this system, lots of connections. But as a proof of principle, it worked. Let me show you how it worked. So the first step is we want to shape the photon. This is not strictly required, but it's a bit easier to run in reverse with a symmetric photon, because then it's truly just the time inverted process. So we did our best to emit a photon and make this wave packet look symmetric. I don't know if you remember before, but it was a little bit lopsided to the right. Here we're able to shape it, and by some metric, it's maybe 97, 98% symmetric. And here's one going in the other direction, and again, it's 96-ish% symmetric. Okay. So the directional absorption protocol looks like this. We, again, are going to create this entanglement up top. We have an entangled state. Now this time, we simultaneously drive the entanglement down to the emitters, and at the same time, we're driving these couplers to absorb it back up on the other side as this photon is traveling over. Okay, and then we're going to measure what happens up top. Okay. There are a lot of parameters, 73 as a matter of fact. There's 6 baseband frequencies. I won't read through them all. There are a lot of parameters, and Aziza and Beatrice did a lot of work tuning them by hand and then decided there's got to be a better way, and that is to use reinforcement learning, okay, which we did. So the idea is to choose a calibration for some of these parameters that you think is at least close or maybe inspired by some physics that we know. You then use a computer to choose another candidate. You then actually send that candidate down. You collect data, and by some cost function and reward, you update a neural network, and you just keep iterating this. This is called one epoch. And as you do more and more epochs, you find that your calibration is getting better and better and better, and then at some point it saturates. So this is training this reinforcement learning. This is how we did this experiment, and it's based on this work by Leon Ding and Max Hayes, where they were able to use a similar reinforcement learning algorithm to get 2-qubit gate fidelities above 99.9%, published last year. So let's look at rightward photon absorption. So we're emitting a photon from this emitter module, and we're going to absorb it on the absorber side. So the first experiment is, let's not absorb it. Let's intentionally not absorb it, and we're just going to let that photon go out to our detector at room temperature. We see it on the right. It looks pretty symmetric, good. We don't see too much on the left, maybe a little bit here because some of it gets reflected. But by and large, we sent the photon to the right, and we detected it. The next thing is, let's turn the absorber on and see what we see at room temperature. Well, now we don't see anything on the right, and we don't see anything on the left, so it must have gone somewhere. And so what we do is we then measure these qubits. We'll first measure the qubits 3 and 4 as a function of time as they're emitting the photon, and so they eventually relax back to 0. And then we look at qubits 7 and 8 and see how they absorb the photon and turn on. Now ideally these should be the same. They're a little bit different. We're working on that. And in fact the other direction looks better, and I'll show that in a moment. But indeed we're absorbing that photon over here now. And the maximum absorbed population was about 63%. If we do it in the other direction and we send that photon back, now you can see that it absorbed more symmetrically on the left side. And it must be related to some of the calibrations that we're doing. Okay. So we can now do absorber state tomography. So we're looking at, here's a leftward photon, here's a rightward photon, and we're just doing state tomography of what's absorbed. And based on that, we can make a budget for where we have errors. So first is that there's just incoherent loss due to propagation. That turns out to be about 16%. We have a lot of coaxial connectors that we would never use in a real experiment just to do this. The decoherence gives us about 10%. We can improve that. We know we've got a directionality error of a few percent. We're working on improving the missed absorption error. Altogether, the Bell state fidelities are about 0.6. The concurrence is also about 0.6. That's above the threshold of 0.5. These are truly 2 entangled modules separated on different sides of the thermal finger. Okay. And the error budget is about 32%. So roughly speaking, we're up at around 90, 93% if we accounted for all this error. Okay. So then the last experiment, and then I'll stop, which is remote entanglement, which is that we would love to entangle these two, or these 4 qubits in the absorber and the emitter module, because now we can do remote gates. Okay. So we do what I just described, except we're going to stop halfway. So rather than emitting a whole photon and absorbing that whole photon, we're going to play that trick we played before with the square root of swap gate. We're going to stop it halfway. So whether it actually went or not, that's part of the entanglement. And these 4 qubits are now entangled together into a W state, where you can see that the 1 keeps shifting over one spot from qubit 8 to qubit 7, qubit 4, qubit 3, all in a single state with some phases. Okay. And so when we do state tomography of that, we find that it's similarly about 62%. And that's true whether we're doing it to the left or to the right. Okay, and again, so these are entangled. So this is the status as of a few weeks ago. So we're still working hard on this, and we'd like to now go to a architecture where we're not using coax cables to connect these modules, but it's all on the same chip using flip chip bump bonding. Just to highlight this again, the 2-qubit gate that we have here using Fluxonium. We now have more than 3 nines, 2-qubit gate fidelity. This is really good. Recent results, which we're preparing now, is we almost have 5 nines for the single qubit gate. And I won't have time to talk about how we did that today, but it's basically by driving 2 quadratures at the same time. So it's basically emulating circularly polarized driving or circularly polarized light on our qubit. And this allows us to get rid of the counter-rotating term. Okay. But what I do want to say is that we are also focused on larger qubit arrays. Here's a 16-qubit device, a 4x4 array. And you can see that it's getting quite crowded at the edges, all the wires that we need to get in there. And that's why for about 10 years we've been working on 3D integration, which is really critical if we're going to realize systems at scale. This is just a cartoon to show qubit chip, an interposer, a readout chip, and you can stack them all together using indium bump bonds in a way that protects the qubit coherence, because it doesn't see anything different than it did before. It sees more of this gray, which is high resistivity silicon. You end up getting some benefits. There's another plane to work with. And superconducting through silicon vias is part of this. And so this top chip would be this, and we're doing experiments where we're doing this flip chip, and it's working quite well. But I'm definitely out of time. So let me acknowledge the team. This is the Engineering Quantum Systems group at MIT campus, and also our sister group out at MIT's Lincoln Laboratory. And let me acknowledge our many sponsors who make it possible, and also thank you for your attention.
Hello, Alejandro Ponte here. I would like to ask you a question about that 16.4 propagation loss in the coaxial cable. Okay. You hinted at it a little bit, but would it be possible to pry a little bit more information on how you want to mitigate that loss over time, especially as it is connecting to different modules?
Yeah, absolutely. So, that coax cable, you've got a wire bond that goes to a K connector, that goes to another K connector, and then another one, and another one, and another wire, right? So it's just death by 1,000 cuts. The way that we would want to do this in the future is to have a multi-chip module. So you basically have a platform on which we're going to place many chips. And each chip is basically a module. And then we're going to talk with each other via this 3D integration that we just showed. That's the idea, how to get rid of that 16%.
Would it have to be that bigger chip? Would it also have to be part of a waveguide to kind of lean the modules into them?
Yeah, in fact, the waveguide would be running around in that lower, exactly, yeah.
Thank you, by the way.
Thank you.
Thank you. One of the presentations we saw yesterday, there was a discussion on cosmic radiation, cosmic rays. affecting qubits. I know you didn't talk about it here, but I know your group did research on that. I just wanted to find out, because I'm doing an article on underground labs, to find out, are we going to see quantum computers being put underground, or are there any new insights you are having, and what could be the impact of cosmic radiation on all these things that you're working on at this point?
I'm sorry, I'm having a little trouble hearing. Could you say it again, please?
Oh, I was saying, I wanted to, one of the presenters yesterday talked about cosmic radiation and its effect on cosmic radiation.
Oh, radiation.
Yes.
Yeah. Oh, I see. Yeah.
Cosmic rays, their effect on qubits.
Yeah.
And I know your group has done some work in that direction.
We have indeed. So yeah. So cosmic rays, they're high energy muons by the time they get to us often, and they basically cause an earthquake in the substrate. Right. It hits the substrate. And that creates phonons, which then interacts with superconductors, creates quasiparticles, and quasiparticles take energy from our qubits. And so this happens, and you can see the decay rates immediately go up, or the T1s go down. Worse is that it happens everywhere on the chip. So there's correlated errors. Not only does it happen on qubit 1, but it's going to happen on qubits 1 through 16 at the same time. That's a problem for error correction. So we've done that experiment to show that matters. The other experiment we've done is by doing gap engineering of the superconductors. You can make a superconductor thicker or thinner, the film, and that will change its gap. Or you could just use a different superconductor, niobium versus aluminum. And by doing that gap engineering, you can actually prevent the tunneling of quasiparticles across the junction. And so the quasiparticles are still there, the muons are still coming, but the part that takes the energy, the tunneling, we block it. That's very fortunate, as otherwise we'd all have to go deep underground. and that probably would prevent commercialization at a large scale of superconducting. So there may be other things that prevent it, but fortunately cosmic rays probably aren't one of them.
Can we have the next speaker come up?
Thank you, Will. Great talk, by the way. Many of the processes that you have told us about in this talk rely on having, I would say, perfect control over the relative phases of the 2 qubit state, or many more qubits, depending on how we want to scale the system. I wonder, what are the main challenges that you experimentally experience when trying to have this relative phase equal to pi over 2, or in terms of precision, what are the main challenges that you saw?
Specifically for controlling those qubits?
Their phases, so that we have perfect constructive and destructive interference in one side or the other.
Yeah, so one reason I showed these single qubit gates is because that's an indicator of how well we can do a particular phase. And we'll never do it perfectly. It's only degrees of how close we can get to unity on the fidelity. But if we get to close to 5 nines, then that means we're limited by other things. And so the single qubit control and some of these phases should at least be at that limit. Now, there are other phases there which were related to a 2 qubit gate, right? And that's another reason why I showed the 99.92% 2 qubit gate. And we still need to keep improving these fidelities. Fortunately, though, we can implement quantum error correction once these fidelities get to this level, or maybe a little bit better. And we need to be at 1 part in a trillion to do commercial large-scale quantum computation. And we very likely will not improve our qubits to 1 part in a trillion. But we don't have to do that, because with quantum error correction, we get exponential reduction in the error rate for only linear or polynomial reductions in the physical qubits. So if I can make my physical qubit 10x better, depending on the size of my code, I could make my logical error rate orders of magnitude better. And that's very likely how it will happen. Yeah.
Perfect, thank you.
Great, thanks for the question.
Okay, we'll take one more question, and then while we switch off the laptops.
It's very quick. Thank you. What's the relative benefit of going underground? Thank you. Sorry, my name is Danielle Speller.
Oh, hi, Danielle.
Nice to meet you.
You too.
What's the relative benefit of going underground versus the mitigation that you found for making that?
Oh, yeah. So with these high energy muons or cosmic rays, turns out you don't have to be just a little bit underground. You have to be way underground. We're talking like, deep, deep, deep underground. And so it just becomes impractical to think that, we're going to have thousands and thousands of quantum computers, that are, thousands of feet underground or more, right? Or thousands of meters even. And it just becomes expensive and therefore impractical. And if there were another solution, people would gravitate towards that other solution. So whereas changing the thickness of my metal so that I can do the gap engineering, that's just growing a different thickness metal, and we grow metals all the time. And so it's much easier to do the gap engineering than it is to imagine digging, a deep hole or, going to a mine or something. Yeah.
Well, I was wondering if you could just give, if it's comparable or if the opportunity cost. We do underground experiments a lot, so I'm just wondering how much you were, either if you were winning by not doing it at all, or if you had for within an acceptable.
That's a great question, and I don't have the answer to it. I think people are doing these experiments right now, both underground and also the gap engineering, and both. Some people are doing gap engineering underground, right? So I think it's the full matrix, and we'll see where it lands. I don't know for sure.
Thank you.
Yeah, thank you for the question. Hey, Marco. How are you?
Okay.
There it is.
Thank you very much for that wonderful talk and for all the excellent questions given by the audience. Up next, we have Professor Marco Longcard, who is who's a professor of electrical engineering here at Harvard's SEAS School of Engineering and Applied Sciences, and we will learn about optical interconnects. So,
all right. Hello. Thanks, everybody, for coming. I'd like to share a few thoughts on optical interconnects that could be used to provide connectivity between various types of qubits, including those that Phil just talked about. And I'm going to mention some of these ideas towards the end of the presentation. Basically, this kind of optical interconnect, by the way, we are a photonics group. In my group, we study optical communications in classical and quantum domain. And so in classical domain, you know that whole information technology basically is based on our ability to connect computers and via computers, people and various gadgets using in particular optical fiber to go over very long distance. More and more optical fibers and kind of optical communications are finding its way in data centers for enabling larger bandwidth and smaller latency, and also reducing the power consumption of data centers because they are actually pretty energy costly. And also actually for wireless communications, like for your cell phones and 5G and emerging 6G application, actually signals are often routed from antennas, from the tower antenna to the base station using optical fiber. So optical communications are essentially everywhere. And that keeps me and my group employed for the most part. But one big issue with this optical communication is security. Basically, the way we send information, for example, over long distances, we take laser, not too different from the one I'm using here to point on the screen, except it's longer wavelength, so it's not really visible. It's 1.5 micron wavelength, which is where the fiber have very low propagation loss. And then we turn the laser on and off. And because there's a whole lot of power in this laser signal, somebody could tap in and steal a little bit of light and essentially eventually break the code we are potentially using quantum computers. All right. So apparently, I've been told that already ongoing is that a lot of the data that's being communicated in the classical domain across over long distances using optical fibers, not using lasers, that they use various security codes that are very, very hard to decrypt using classical computers. But if you store all of this data and then eventually take one of Will's quantum computer, you could potentially decode all of your secrets that you're sending left and right these days. And so the idea is to actually replace this classical communication channel using quantum communication channels that we protected by laws of quantum physics. As essentially, we also use photons like Will. Our photons would be, though, of much higher energy, so they can propagate with very low loss and with little susceptibility, if any, to noise. And so essentially, they can travel quite a distance. And basically, then if somebody eavesdrops, if somebody takes your information, if you essentially encode information you're sending in a single photon using kind of various degrees of freedom of a photon, polarization, time, frequency, whatnot, you actually can protect this information. So if somebody eavesdropper wants to like tap in your communication channel and wants to hear what you're doing, actually you would be immediately able to detect that and stop communication protocol, change the secret key, and then continue communicating. And this is kind of one of the ideas, one of the motivations behind this ultimate goal that some of us are aspiring to, which is the quantum internet, which will be kind of quantum version of classical internet that we are all using and love these days. And so basically here, not only it would be secure, but more importantly, especially in the context of what Will was talking about, if we are to use this quantum internet to connect not classical computers securely, but also quantum computers, these links, which will for sure going to be made out of optical fiber. So there's some very interesting proposals how this could be done in free space using tunnels of various sorts. But if you stick with optical fiber, then basically what is needed to connect quantum computers to this fiber link, you need essentially quantum modems, right? Just like your electrical computer needs some sort of modem, we call them these days transceivers, that to take the electrical data to optical domain and back from optical domain back to electrical domain, you will need devices like that in quantum space. And these are called quantum transducers, and this is one of the things I'm going to tell you about in this presentation. Another component that I'm going to tell you a little bit about, or rather components of these components, are quantum repeaters. And so these are devices that are there to fight the loss of the optical fiber. So optical fiber is very low loss, but even in classical communication world, you cannot propagate forever, and they use a lot of laser power. When your optical signal is attenuated enough that you can actually not decode information anymore, what you do, you amplify it. You put an amplifier, erbium doped fiber amplifier, for example, you amplify it, and then you boost your signal, and you continue propagation. In the quantum world, that's not possible because of essentially no cloning theorem that says you cannot copy quantum information, which is why it's secure in the first place. So what we need are these kind of relays, as I like to refer to them, of quantum information that essentially rely on distributing entanglement over a long distance. Okay, and so we'll talk quite a bit about entanglement. I'm sure I missed a few talks in this conference, but I'm sure there was a lot of entanglement discussion. So you're experts on entanglement, so I'm not going to try to explain it. I wouldn't know how to, but anyways. In order to preserve entanglement, first establish it and preserve entanglement, we need to have quantum memories. Okay? And so my first part of my talk is going to be focused on these quantum memories. Basically quantum memories that will allow us to make quantum repeaters. And so, and this is a little broader overview what my group does. In context of this presentation, I'm mainly talking about photonics that can be used to make quantum memories in diamond. I will not talk at all about ways to use phonons. Will mentioned the phonons can be actually really bad for quantum, which is absolutely true. We are trying to turn this upside down, actually use phonons, us and many other people in the community, use phonons as information carriers to actually try to have them do something useful, but I won't be able to tell you anything about this today. And then in the second part, I'll talk a little bit about quantum photonics and this other material platform we've been working on. It's called thin film lithium niobate. It's a mouthful, but I'll explain what we mean by this and why it matters. And then towards the end, unless Bill cuts me off, then I'll tell you a little bit about quantum transduction. Oh, okay, all right. I'll make friends with you. Bill, you don't matter anyway. Okay, all right. So how does quantum communication work? How does quantum memory work? We need long-lived quantum memory, okay, that can interact with light. So quantum states will be stored in this quantum memory where we are trying to establish entanglement across long distance. Because atoms are very small and light photons wavelength of, let's say, 700 nanometer or ideally 1.5 micron wavelength is pretty large. Interaction between light and atom is not very, okay, here we go, is not very good. And therefore we typically put these atoms inside optical resonators so they can actually interact. The light has higher probability of interacting with an atom. And so this is a node of the quantum network. And so then on the other end, we would have another, actually, let me show another node. We have another node of quantum network that also has quantum memory, an atom, or it can be, in our case, artificial atom, which is defect in diamond. And that, as long as it can be communicated with using light, we're good. and basically then these two couple using fiber links. To extend coherence, to extend essentially, to store the information for a longer period of time, we often use also auxiliary memories, like a nuclear spin in solid state in our case, whereas this communication memory would be electron spin in diamond. Okay. And so in order for this to work, a few things already are apparent. First, I need to have emitter. I need to have memory that can talk to light. So that's one thing. Second, I should be able to make very good cavity around this emitter in order to enhance interaction, because otherwise interaction is weak. And I need to be able to make two atoms that look almost exactly the same so that these photons are all indeed red, right, as illustrated here. They're the same wavelength, the same frequency. Otherwise, if they operate slightly different wavelength, then this communication is not going to happen. And this is actually one thing that's actually pretty hard to do in solid state. It's very easy to do it with real atoms and trapped ions. It's very hard to do in solid states. It's maybe not so hard to do in superconducting quantum computer because everything is a little bigger, but in the systems we are working with, this is actually very difficult. I'll tell you more about that. Okay, and so our memories, as I mentioned, are color centers in diamond. And so thanks to Bob and his wonderful Science Technology Center from a few years ago, we got this beautiful movie from Museum of Science that shows basically diamond lattice that consists of carbon atoms that then we make these defects by essentially we take one carbon atom, replace it with nitrogen, and then nearby carbon atom is knocked out. This is vacancy. And this complex nitrogen vacancy becomes actually negatively charged, traps one electron. This is this cloud. And then we can store information to the spin of this electron. Okay, this is the idea. So now we do not use NV centers anymore, but this is the movie I have. So what we use is we do have silicon vacancy, but it's not as fancy. We use silicon vacancy. I can tell you why we don't use NV centers in communication. NV centers are very much used in sensing, and they're probably sensing talks here. Here, no, I'm here. Maybe Natalie may talk about NV centers, perhaps. No, okay, all right. So for sensing applications, they're actually workhorse. For quantum communication, community has switched to silicon vacancy, which basically look more or less the same, except instead of nitrogen, you have silicon, and silicon sits between two vacancies, and that's your silicon vacancy center. It has a little better properties. Oh, wait. These guys, this is dramatic. Hold on, let me turn my sound on. So essentially, we don't use commercial diamonds. We don't use man-made. We don't. I got reset here while doing this. We don't use natural diamonds. We use man-made diamonds that are commercially available. Though actually, like groups like Tina's group and other groups around the world are able to make these very nice, high-quality diamonds in a lab. And so basically what you have methane coming down a diamond substrate, and then essentially you lose hydrogen and carbon goes down a lens. Bang. Amazing. It took me a little more time to prepare this movie. Okay. And so, all right, this is a carbon. And then you can dope this chamber with a little bit of nitrogen. And so this is, and then you need to anneal the whole thing, and you need to actually create some vacancies to make these nitrogen vacancy centers. So now that we change our this is how it looks like when you illuminate this diamond with nitrogen vacancy center with green light, you get a lot of red light. So now that we are using silicon vacancies, I need to make a whole new movie. It's probably harder than doing experiments with silicon vacancies. Anyways. So this is how it looks like. And so, but normally when you get these samples, and this is pink diamond, by the way, so its color comes from a bunch of NVs inside. So you can excite them with green and get a lot of red light out, but actually the problem is the diamond has very high refractive index, so you don't get all these photons out. In fact, only like about 5% of light comes out, if that much. And so over the years, us and others have looked into ways to improve collection efficiency of light coming out of diamond, and in the process made CNS rich, I'm guessing. I spent a lot, we are really lucky to have CNS famous. Okay, wow, thank you. And so basically, the first thing that we looked into how we can actually shape these diamonds so that we can get more light out. And the kind of, I wish I could say we drew inspiration from, I guess I did say it, from nature, but in reality, this is just standard fabrication process where if you have some sort of hard material on top and then you expose your substrate, in this case, planet Earth, to the elements which erode the material, you end up with these pillars. Well, if you take diamond and put it in a reactive ion chamber in CNS and protect a little bit of diamond, in this case aluminum oxide, and expose it to oxygen plasma, you essentially carve these diamond nanowires very easily. And so we have done this, why is this good? Because then we center, then when light gets emitted, light can get trapped into this waveguide and very effectively collected. We do lose 50% of the light off the bat, but that's why we have a few other tricks that I'm going to share with you later. And here we just collect the light more efficiently. We don't produce light more efficiently, which is another thing we would like to do. So if I use this in a quantum memory node, this wouldn't work very well because there's no resonator. Photon would just pass once, and that's it. So I want photon to bounce back and forth. So I need to put some mirrors on the top and bottom. We can make this at scale, and this has been a lot of fun. But also, as I said, they're not, except for some applications that my colleague Amir Yacobi and a few others around the world are using them for sensing. These haven't really been used a whole lot in quantum communications. Because we said already we need resonators. In acoustics, if you have different types of wire that resonates, in order to amplify the sound, you need to trap this sound in some sort of resonator. And so this is in optics, the way we make resonators, as many of you may know, we put essentially mirrors. So you need to have very high mirrors to trap the light and allow light to essentially interact strongly with this color center. Mirrors can be made of metal. They actually are not good enough for what we need. They are actually quite lossy. Or you can make mirrors out of total internal reflection, which actually can work. Or what we can make them based on distributed Bragg reflection, which is what you have in your microwave. If you have periodic arrangements of materials and holes, that actually makes band gap for light, and light cannot propagate through this thing. In this case, your microwave doesn't go out and doesn't fry your head, but the periodicity of this lattice is actually proportional to the frequency, to the wavelength of light microwave that you're using to do this. So again, drawing inspiration from this, you can come up with another arrangement of holes. This is roughly now diamond waveguide. That's maybe micron wide, half a micron thick with periodic arrangement of holes. Actually, when Natalie was here at Harvard, she helped develop this platform. And this is freestanding. And so what we can then trap light inside of these optical resonators, we call them. We can also implant silicon atom. I've told you we are using silicon vacancies, not nitrogen vacancies. And now this thing can actually work really, really well. And also meaning light and atoms can interact very closely. And basically we can bring optical fiber to couple light efficiently. And this is a long-standing collaboration that we have had with Misha Lukin and many, many students, postdocs who contributed to this and also prepared this particular slide. And so this technology has resulted in all kind of neat demonstrations of realizing basically like quantum networks at metropolitan scale. Basically, there are some examples here of two recent examples. One is between MIT, Harvard, and Lincoln Labs, and another one is Harvard and AWS, which is one of the collaborators on this program. Amazon Web Services, basically Center for Quantum Networking. So we demonstrated using the devices that I described you, and basically by experiments in Misha's lab, and Misha may tell you more about this, is that essentially you can establish these quantum links across many kilometers of distance, which is quite nice. Of course, we would like to go from Boston to San Francisco, Los Angeles, at very least DC, so we can communicate to DARPA and other funding agencies securely, so the MIT folks don't steal our secrets. But this is beginning, right? And these rates, the communications are very slow. So there's a lot to be desired for, but this is just nice demonstrations. How do we make these cavities that I showed you? This is not actually easy, and we spent quite a bit of time. I showed you that by just etching diamond, you end up with these beautifully vertical and sidewalls, but also you can draw inspiration from nature like this, and you can turn your plasma a little bit sideways, and then you can etch diamond, like undercut it like this. And if you continue this process, you can completely remove diamond from underneath, and this gives you this freestanding stuff, Right? Freestanding devices essentially is just erosion by forcing ions to go underneath to attack your sample at an angle. That's one way how you can do it. And another way is basically just like, instead of rain coming from an angle, here you have essentially this waves going back and forth. So you could do the same in a reactive ion etching chamber. Basically, you put your diamond substrate with mask on top of it, and you control condition in diamond in the chamber so that plasma actually doesn't eat diamond vertically but laterally. And you can see a progression. These are three snapshots taken one after another. There's many hours of work in between, but basically you see how this region underneath becomes more and more clear. And when everything's said and done, you end up with this kind of optical resonator that is completely freestanding. And so now you have this diamond resonator that sits on diamond substrate, and life's good. And you can use this to make various devices. And this is all nice, and then this is very kind of diamond specific. In all other photonics platform, what people prefer to do, or what people typically do, they actually use so-called thin film technology, right? So you have thin film of the electric material, like silicon on insulator perhaps, or like gallium arsenide or indium phosphide. And then basically, as long as material you're interested in has higher refractive index than your substrate, you can confine light in this layer, and then fabrication becomes much easier and devices get more and more complex, and you can end up doing stuff like similar to what Phil was saying, just at optical frequencies. In diamond, unfortunately, that's not possible because you cannot buy these thin diamond films. And despite me trying to convince many people to do it for years, actually it's been like very hard to do. Though there was some really nice progress I'm going to share with you that we are quite excited about. But in an effort to make our own thin films, we have also did this so-called brute force approach many years ago. We take a piece of diamond, put it in a reactive ion chamber. This piece of diamond is maybe 20 microns thick. We put it in the chamber, thin it down, and then essentially till it becomes about micron or 0 microns. If you get carried away, then you don't have diamond anymore. And then you can make your devices, and we were able to make beautiful devices in this approach. These are some of the nicest diamond rings, to me, at least. But the problem is that these diamond films, when you etch them, they're really not uniform. There's all kind of technical issues. That's why we abandoned this process many years ago in favor of what I showed you, these angled etching and isotropic undercut. Recently, we started working with a colleague of ours, Alex Hai, who was also a postdoc at Harvard, actually, with Hong Kong Park and Misha. And so he and colleagues in Argonne National Lab have developed a very nice process to make these thin diamond films. I'm not go into details, but now we have these thin films of diamond that are beautiful, uniform, have very nice color center in it, and more importantly, they can be transferred on any substrate we want, like silicon dioxide, whatever you want. We like silicon or silicon dioxide. And then you can start making these interesting devices like 2D photonic crystal waveguides. This is now a thin diamond membrane, or you can make these optical resonators as shown here. All of these are, except for material itself, all of these are made here at Harvard and CNS, and you probably will see some of these tools up close and personal. This is for kind of maybe specialists in the audience. I don't want to spend too much time on this, but some of these thin film diamond resonators have some of the highest quality factors, some of the sharpest resonances we've seen in visible wavelength range at around 737 nanometers. They also can host silicon vacancy centers that have very nice properties. And using these, you were able to demonstrate, this kind of, we were able to verify that they are good enough property for our quantum experiments. So we are now hoping to take this technology to the level of these quantum network demonstrations, and because this is we'll be able to integrate many more components in this diamond film, and more importantly, this is going to facilitate integration of diamond with other photonics platform, which is very important, as I want to show you in the next few slides. So not everything is nice in diamond world, like as I mentioned at the beginning. Like we need all of these quantum memories, and if you want to communicate between them, to be exactly the same, so that or at very least, they don't have to be exactly the same, but they need to be able to communicate with the same color of light. And unfortunately, in diamond, due to environment, local strain variations in diamond environment, and many other reasons, actually, we have something called inhomogeneous broadening. It means each silicon vacancy center or any other color center in diamond or any other solid state material they all look a little different. They all operate slightly different wavelength. And that's bad because then you cannot do these quantum communication protocols. So there's a number of ways how you can address this. One of the ways that we looked in the past is we made these diamond cantilevers, and we put color centers inside diamond cantilevers. And as we strain diamond cantilevers, you can actually change the color of a light that gets emitted. This is due to the fact that just the particular inner construction of silicon vacancy, Y actually can change the emission by applying strain. Not every color center gives you that feature. And using this, we were able to show that you can take two silicon vacancy centers in the same waveguide and have one be tuned, another one don't be tuned, and basically shows their emission wavelength as a function of voltage we apply between these two electrodes to induce amount of strain, and we can bring them in resonance. And this is Bill was telling you, beautiful experiments you can do when you have two atoms that are coupled with a waveguide. In our case, atoms are silicon vacancies, waveguide is based on diamond, but we need to go to great length to actually bring them so they can talk to each other. So this is one of the problems, and this was one of the solutions to these problems. There's a few other problems that are needed, and one is that, for example, first is silicon vacancies look different. Second, silicon vacancies emit at 737 nanometer wavelength. That's pretty much red. For long distance optical communications, we need 1.5 micron light. So we need to have so-called quantum frequency conversion. Something's going to take us from red to telecom wavelength range where optical fiber are very low loss, or at very least 1.3 micron wavelength. And another thing is also the rate, entanglement rate using silicon vacancies is not very high. So we need to actually multiplex. We need to try many, many times in time, in space, in frequency, any way we can to establish entanglement to have appreciable rate over long distance. For this, we need to actually integrate many different quantum memories on the same chip. And it's not going to be necessarily possible to do it with diamond. And we decided, as well as the community, that probably we need to do some sort of heterogeneous integration, meaning we probably have to make some photonics platform that's going to provide all of these different functionalities, changing the color of photon, multiplexing different photons, changing when these photons get emitted, how they look like and whatnot. And diamond just going to be essentially serve as a memory, host to memories, right? And so in our case, this kind of material platform we opted for is lithium niobate material platform. How much time do I have? It's going slower than I anticipated. Who is?
Let's say 10 minutes,
15
15 minutes.
to 20, got it. Okay, no, 15. Yeah, okay. Well, I'll take coffee and, yeah, okay. All right, so lithium niobate is actually old material. It's actually been referred to as a workhorse of optoelectronics because of these wonderful properties, and most important one is the second order nonlinearity. Okay, and so second order nonlinearity means means several things. They're all illustrated here. It means you can change the color of light. I can send 1064 nanometer laser into lithium niobate, and out comes green light. So this was actually used to make very high power green laser pointers. It can be used to make photon pairs, which is of importance for quantum communication protocols, not of a kind I'm talking here, but we are working on that as well. And it's used to make modulators. These are electro-optic modulators. These are devices that actually impart electrical information on top of your optical carrier. Okay, and so these are the ones that these modulators that are in transceivers. This is electro-optic modulator that sit in transceivers that actually are used for long-distance communication. So now, unfortunately, lithium niobate is also a very difficult material to work with, and people for years have tried to integrate devices in lithium niobate, but they have remained bulk components because it was very, very hard to etch lithium niobate, and also thin film of lithium niobate were not available. And so a few years ago, actually, there was commercial development. Like first thin films of lithium niobate were made in Colombia some years ago. And then there's a company in China that has emerged that's actually commercializing this thin film lithium niobate technology. Basically, you can now buy thin film of lithium niobate, about half a micron on top of oxide, on top of silicon, that allows you to do all fancy photonics. If you could only etch devices in it with so that they have very, very low loss. And that's something that actually community struggled with for years. And then actually maybe about 10, 15 years ago, actually we started looking into this, and thanks again to CNS being adventurous, letting us put all kind of neat materials in the chambers, we were able to optimize the process that gives you extremely smooth sidewalls of these lithium niobate waveguides that leads to extremely low loss. So these losses are about 3 dB per meter. That means as you propagate 1 meter, you lose half of your light. And these chips are roughly centimeter scale. So essentially, from one end of the chip to another, you almost lose no light, which is very important for quantum information processing. We have made some of the first thin film lithium niobate modulators using this approach several years ago now already. And these were actually, they kind of blow out of water anything that's on the market in terms of how fast they can be operated, how little energy they consume, and how little loss they have. They are also a little more expensive than incumbent technologies, but this is, I think, a matter of technology development. And also a few years ago, we started this company, Hyperlight, that's commercializing this technology, and I encourage you all to actually seek jobs there. It's actually pretty big. It's about 40 people right now, and so they're already making these are transceivers. These are the pluggables that actually go into your computational servers. On one end, you have fiber, on the other end, you have electronics, and inside you have this modulator made of lithium niobate that is turning signals from electrical to optical domain. And this technology is now wafer scale, done in commercial foundry. So it's really something that works really, really well in classical world. And the question was, is this going to be good enough for quantum world? And so one of the first things we wanted to do was actually address this issue of inhomogeneous broadening. We wanted to basically take 2 silicon vacancies and make them look the same. I have silicon vacancy that emits 2 different colors of light. What I can do, I can fix color of light for one of these photons. And the way I can do it is I can use something called spectral shearing, right? So basically, if I make phase modulator out of lithium niobate, okay, essentially I have lithium niobate waveguide with some electrodes, and I send RF signal along my electrodes. Due to this electro-optic effect, as I apply voltage, I change refractive index of material. Because of that, the speed of light changes, right? So I apply voltage, speed of light changes. That means signal accumulates different phase as it propagates. So if I can actually have my signal, my photon, be surfing essentially microwave signal. So I have here on a gold electrodes, I have RF microwave signal, and blue is optical waveguide. If microwave signal and optical signal propagate at the same speed, then essentially it looks like optical photon is surfing on top of microwave photon. And as it does it, it constantly changes its phase, basically. As it propagates, changes its phase in a linear fashion, if you do it right. And that essentially change in the phase in linear fashion is the same as shift in frequency. So this allows us to actually change. We put photon that looks like this, and this is not silicon vacancy photon. But these are single photons at telecom wavelength. And we send these photons to phase modulators that's surfing on this side of the wave or on that side of the wave, rising or trailing side of the wave, a microwave wave, I guess. Then you can get the color of this photon to be shifted down in wavelength or up in wavelength. Okay, about 600 gigahertz. We have done this also. We have done this also in a 2 slides down. Maybe I'll just show it right away. We have done this also at 737 nanometers wavelength. It actually works even better. This is original photon packet, but this is done with classical light, not with single photons yet. And so we can, again, depending where we park this optical photon, increase its frequency or decrease its frequency. And the best we can do is about 15, 20 gigahertz, which is plenty enough to overcome inhomogeneous broadening diamond color centers. And so why we are doing this is because we would like to come up with a basically heterogeneous integrated photonics platform that looks like this, that has lithium niobate that is used to modulate light, to prepare optical signals. Laser light comes from here. We can turn this laser light on or off. We can actually make pulses. We can do all kinds of stuff. Then we have a little bit of diamond here that serves as a host for the memory. Then after this diamond emits light, we can have, again, modulators to fix the color of this light, basically. And then we can have many of these devices on the same chip and multiplex them using what we call the switch fabric. So basically just a bunch of beam splitters that come together to the same optical fiber. So this is the vision that we would like to do. And this, as you can see, I don't have time to go through this. This actually can give you increase in the rate of communication rate by several orders of magnitude, because simply you have they're trying at the same time to establish entanglement with very many different memories in parallel. And then you use the ones that actually do click that make entanglement. So you end up using those color centers. Okay, I'm out of time. I'm just going to tell you that, and Hannah, I saw you Hannah somewhere. If you can ask Hannah for if you have questions about this, but this relates very nicely to what Will was talking about. One day when, because we have quantum computers right now, and if you want to scale them up, if you want to have more and more quantum computational power, actually cooling power inside the one dilution refrigerator where these things operate is not sufficient at the moment. At least what I've heard from the community. And basically, you cannot put very many qubits inside one dilution refrigerator. So you can build bigger dilution refrigerators, or what you can do, you can try to do modular quantum computing, where you have two quantum computers that are separated by distance and connected with some link, quantum interconnect. Now, these superquantum computers operate at microwave wave frequencies, but microwaves don't go very far, and they attract a whole lot of noise if they are not cooled. So idea is to actually replace these links using optical fibers, but then you need quantum modem. You need to have what I like to call the most efficient modulator on planet, which is going to be a lithium niobate modulator that can be turned on and off with single microwave photon. Okay, so this is the best you can do. And so the way we do this, similar to Will, actually, we make these, we call them photonic molecules. We take two resonators, optical resonators, we couple them instead of two qubits, as Will was talking about. And they essentially hybridize, they make supermodes that we use to do this transduction. How we do it, I'll let you ask me or not. This is I'm just going to say, this is the lithium niobate structure that Hannah has devised that works really well, and using this in collaboration with Rigetti Quantum Computing and also some folks that are now in Will's lab and going forward. We are going to continue working on this transduction protocol. Basically, the moment efficiency of this transduction process is about 1%, which starts to be sufficient to actually start doing some interesting stuff. We think we can get to about 10% relatively easily. Well, easy for me to say, but But then maybe I'll skip this. Okay, this is not working anymore. But it's basically technological achievement. And if you swing by a lab, you will see this fridge. This is how it looks like. So basically, these dilution refrigerators at the bottom. We also have a whole lot of optics because we want to couple superconductors to light. We have done this. And this is Hannah and CJ happily working on the fridge, so you can talk to them. And I think a few other people from my lab are here. But what was the highlight experiment that Hannah has done recently is she used light. So, and Will and I use light in different contexts. Our light is 200 terahertz, right? Light that we see. We use that light to control superconducting qubit, right? That are typically controlled by microwave signals. So we use light to do that. And that's actually quite enabling, but I won't be able to tell you why. Anyways, so this is a summary. And I'd like to thank the team and collaborators and funding sources and you guys for attention.
Thank you for the excellent talk. I guess we'll go around and ask questions.
Hello, Rilas, fifth year PhD at Clark University. Thank you so much for the talk. Yeah, I have a question regarding the diamond etching part of your talk. And it seems to be tedious to do the etching part of the diamonds to get a certain shape. And I'm wondering if there is maybe another way to do that using nano diamonds or micro diamonds embedded into like a polymer like PDMS, which is flexible substrate, and we can get like any shape we want, like pretty easily.
Yeah, great question. We think going forward, if we can get enough of these thin diamond films, this is going to become as easy or as complicated as any other photonics platform. But absolutely, you're correct. Now, all the gymnastics we do with etching so far is not easy to reproduce. Well, easy to reproduce, but not easy to get there. Over the years, we looked into nanodiamonds, we looked into plasmonics, we looked into heterogeneous integration, and that's actually something that rare earth ion community is using today as well. We didn't, well, I haven't. I think community has looked into probably there was definitely nanocrystals on top of silicon nitride and microtoroid resonators. I remember work from Oscar Painter from many years ago. You could probably put it in PDMS, but then you would have to make very good optical resonator in PDMS. And that's not impossible. We have made nice resonators in low index medium. In fact, with Hong Kong, we had paper a long time ago making actually stretch tunable PDMS silicon cavities. So, tuning would be good, except that it has to operate at millikelvin temperature, so it wouldn't. So that's probably why you shouldn't do it. I don't know how PDMS looks at the millikelvin temperature. Yeah.
If I can interject a question here, what is the ultimate limit, or what do you expect is the limit for transduction for photons?
Ultimate limit, I think, is 100%, but kind of so good, maybe 101 even. I don't know. I think we would. It's hard. Like people have demonstrated in community using less scalable, but more kind of physics type of experiments. Efficiency maybe 30 to 50% already. We can, I think there's nothing that says that we shouldn't be able to get there. There's also protocols that are not direct transduction based, that are kind of entanglement teleportation based, that are actually can tolerate some of these losses. So I think we are basically quite ready to do some kind of really interesting and potentially useful demonstrations.
Thank you.
Hi, James Raton, fifth year chemistry PhD student at Yale. Also interested in the diamond cutting process, but more for like a two-part question. The first was, is the only hole or like cavity you're able to make with these diamond cutters only able to produce 736 nanometer light?
So is this the first part?
Yeah, that's the first one. Is it only able to produce that wavelength of light?
So the color of light comes from the defects that we implant. So we normally take these days. I show you the movie, maybe somewhat misleading, is old version of the process. We would ingrow emitters. Right now we take pristine diamond without any nitrogen, and then we implant whatever color center we want. And there are color centers for diamond that operate almost everywhere in a visible spectrum. Not all of them have excellent quantum properties, but that's possible. And then our fabrication process can be tuned to pretty much anything. It gets a little hard, a very short wavelength range if you wanted to. We have some devices that actually have feature sizes about 100 nanometers, but below that probably would be feature size 20 nanometers, periodicity 100 nanometers. Below that would be much harder to do. And
perfect. That's kind of getting to my second question. Was I'm a cryogenic ion vibrational predissociation vibrational spectroscopist. So we use a lot of lasers, and I was wondering, do you see capacities to use your diamond cutting techniques to make tunable, short limited range diamonds that can produce light for like experimentation usages?
You mean like UV light or something like that, or?
Yeah.
Yeah. So that's a wonderful question. So people have generated UV light. Essentially, the bandgap of diamond is in UV, about 220 nanometers, so you can generate UV light. More common, what people do is Raman laser, because diamond has very strong Raman effect, so you can generate light in a wavelength bands when you don't have convenient lasers, as long as you can pump it, Raman shift away. And then there was a lot of interest in color center lasers, like TISAF is basically color center laser. And there were some reports in diamond that's being done, but it hasn't really taken off as an industry quite yet.
Okay. Let's take a last question, and then we will take a break for the coffee break, and that way we can ask as many questions as you want. One more.
Thanks for the amazing talk. I'm Ipshit, I'm from Colombia. I have a question regarding the integration of the entire parts together. For example, if you have lithium niobate, which is difficult to fabricate, and then you have diamond.
It was difficult to fabricate.
It was, I know. Yeah, and it was difficult to fabricate. Diamond is so easy to fabricate. When you bring them together to make a whole system, it requires positioning of diamond cavities on these areas, because I'm assuming that defines how much efficiency of coupling you can do out.
Yeah, great question. And also, I am embarrassed. I guess I sold you diamond very hard because diamond is actually much harder to fabricate than lithium niobate. But question is perfect. Excellent. So there's a few ways how you can do it. Early and this is I'm speaking on behalf of community. In early days, what you could do, you can make diamond cavity and silicon nitride, silicon, lithium niobate, whatever. Well, not silicon. Platform, and then you pick and place one of these things, right? So that is not very scalable, but there were some very nice demonstrations done using like this approach. We like to do now, and I didn't include in presentation, but this is done in collaboration with Alex Kai's group as well. We make lithium niobate platform, we planarize it, and we can easily do it because it's on a wafer scale. Then we transfer pristine diamond substrate, not fabricated in it, and then because we have markers everywhere, we can just go and make devices exactly where we want them, and then alignment is perfect. And so we have beautiful SCMs and 0 working devices, but maybe in a week, this can change. So it's just a matter of trying. Yeah.
Okay, let us thank both of our speakers from this afternoon session. Okay, we'll take a 15-minute coffee break and we'll resume at 35 minutes after the hour.